Hello and welcome to the channel. As an Australian, I couldn't pass over the contest taking place here. In general, I must admit, the Australian contests are not as strong as similar contests in Russia, North America, or some countries in Western or Eastern Europe. However, this one makes me feel really proud for my country. The problems are diverse, challenging, and beautiful. The 2020 Australian Mathematical Olympiad, organized by Australian Math Trust, took place in February last year, just in time. Had it been scheduled only a few months later, it would be most probably postponed. About 200 competitors from different parts of Australia and New Zealand participated in it. The contest took 2 days, 4 problems per day, 4 hours time limit. This video deals with the first day assignment. All problems have the rate of 7 points, even though you don't need a microscope to find out that they are actually listed in increasing order of difficulty, with the last problem being essentially more difficult than the first one. The official solutions are publicly available, the link will be placed under the video. However, being at limited time, I had a strong advantage over the participants. Why wouldn't I use it? This is what I've come up with. Problem number 1. Determine all pairs AB of non-negative integers such that a plus b halved minus square root of ab equals 1. A math contest should feature a simple problem to ensure that at least one problem is solved by someone. Otherwise, why would they need the contest at all? This problem is certainly the one. Just think for a while and you should solve it without any hints. I start with a statement which is usually taken for granted. But since I decided to be strict here, I will prove it. If square root of a non-negative integer is rational, then it is integer. In other words, a square root of a non-negative integer n can be rational only if n is a full square. So we have a non-negative integer n, such as square root of n is a rational number. This means that n can be represented as an irreducible fraction p over q. So p and q are both integers and coprime, as the fraction is irreducible. The denominator q is obviously non-zero, and we can assume it to be positive, as if q is negative, we can multiply both p and q by minus 1. So the value of the fraction doesn't change, while the denominator becomes positive. From the expression for square root of n, we can evaluate n as p squared over q squared. Since n is an integer, p squared over q squared must be also an integer. At the same time, since p and q are coprime, they have no common prime factors. P squared has same prime factors as p, only their powers are doubled. Q squared has same prime factors as q. Since p and q have no common prime factors, then p squared and q squared have no common prime factors either, which means that p squared and q squared are coprime, so fraction p squared over q squared is irreducible. Since p squared over q squared is irreducible and integer, the denominator q squared must be 1. Since q is positive, then q must be 1. This means that p over q, which is square root of n, is an integer. The statement is proven, and we move on to the problem. Just multiply the equation by 2. Since both a and b are non-negative, we can, without any hesitation, rewrite the left-hand side as square root of a minus square root of b all squared. The obtained equation is equivalent to absolute value of square root of a minus square root of b equals square root of 2. Therefore, square root of a minus square root of b can be either plus square root of 2 or minus square root of 2. Actually, I know a more efficient method to solve these equations, but in order to avoid skepticism of some viewers, I will use a standard approach which suggests isolating one of the square roots. In the first case, I isolate square root of a. In the second case, I do that with square root of b, getting equations 1.2a and 1.2b. You can see that the right-hand sides of both equations are guaranteed to be positive. Therefore, by taking a square, we will not get irrelevant solutions. By comparing 1.2b with 1.2a, you can see that in 1.2b, a and b are just swapped. Therefore, it will be sufficient to solve only 1.2a. Then we can swap a and b and get all the solutions of 1.2b. Actually, this is an expected thing, as a and b appear symmetrically in the original equation. Let's solve 1.2a. We take a square and get the equation 1.3, from which we can get an expression for square root of 2b, which shows that the square root of 2b is a rational number. Therefore, according to the proven statement, the square root of 2b is an integer. And this integer must be non-negative, according to the definition of arithmetic square root, denoted with letter k. Then we take square of the equation for k, from which we can see that k squared is an even number. It can be easily proven that a square of an odd number is an odd number. Therefore, k must be also even. So we set k equals to n, where n is, just like k, a non-negative integer. Substituting the value of k into the equation for 2b, we get b equals 2n squared. Now we can substitute b into the equation 1.3 to evaluate a, where we take out 2 as a common factor, so we get a equals 2 times n plus 1 squared. We have found the solution for the first case, while for the second case we just swap a and b. I hope the tempo wasn't too fast, as this is a standard method and it should be clear even without speaking. Here are the two series of the solutions written in a neat way. As an illustration, I've listed first 3 pairs of each series. Someone may argue that the requirement of n to be non-negative is redundant. Indeed, it can be easily checked that if you take a positive n and replace it with minus n, the result is also a solution, though from the opposite series. However, allowing negative n's leads to duplicate solutions, which I prefer to avoid. The only computation problem in the assignment is complete. All others are about proving. Problem number 2. Amy and Beck play the following game. Initially, there are 3 piles, each containing 2020 stones. The players take turns to make a move, with Amy going first. Each move consists of choosing one of the piles available, removing the unchosen piles from the game, and then dividing the chosen pile into 2 or 3 non-empty piles. A player loses the game if they are unable to make a move. Prove that Beck can always win the game, no matter how Amy plays. Typically, problems related to game strategy are solved from the end. Try to analyze it first and figure out the way to approach it. The correct approach is the key factor for solving the problem. Let's analyze the game first. We are going to fill in the table containing 2 columns. The left column, selected quantity, will contain the number of stones in the selected pile. The right column, split to win, will show how the selected pile has to be divided in order to win the game. The column will contain dash if there is no way to win the game, provided of course the opponent plays correctly, making no mistakes. So let's start filling the table. A pile containing 1 stone cannot be divided and therefore cannot be selected. If all piles contain 1 stone, you lose. Therefore 1 is a losing number and we put dash for it. A pile containing 2 stones can be divided into 2 piles with 1 stone in each. That will make your opponent to lose the game and you win. So 2 is a winning number. A pile with 3 stones can be divided into 3 piles with 1 stone in each. Therefore 3 is also a winning number. Can we win selecting a pile with 4 stones? the pile has to be divided into 2 or 3 non-empty piles. Therefore, each new pile will have less than 4 stones, meaning 1, 2, or 3 stones. However, if there is a pile containing 2 or 3 stones, the opponent will select this pile and split it according to line 2 or 3, making you to lose. For that reason, you can win only if each new pile contains only 1 stone, which makes total number of stones no more than 3. This is impossible for a pile with 4 stones, therefore 4 is a losing number. A pile with 5 stones can be split as 4 plus 1, forcing the opponent to select a pile with 4 stones, in which case, as we already know, they lose and we win. In a similar way, 6 is 4 plus 1 plus 1. Number 7 cannot be represented as a sum of 2 or 3 losing numbers. Therefore, at least one of the new piles will contain a winning number of stones. The opponent can select this pile and win. This makes 7 a losing number. A pile of 8 stones can be divided in one of two ways, 4 plus 4 or 7 plus 1. In both cases, the opponent is forced to select a pile with a losing number of stones. 9 is either 4 plus 4 plus 1 or 7 plus 1 plus 1. 10 is a losing number. This analysis shows that a number is winning if and only if it can be represented as a sum of 2 or 3 losing numbers. Probably you see the pattern. You only need to prove it. We are going to prove the following statement. A player loses if the number of stones in the selected pile divided by 3 gives remainder 1 and wins with another remainder. That can be rephrased in the following way. For a positive integer n, consider 3 sequences. Sequence an equals 3n minus 2, sequence bn equals 3n minus 1, and sequence cn equals 3n. An can be represented as 3 times n minus 1 plus 1, which means that all members of an give remainder 1 when divided by 3. In the similar way, all members of sequence bn give remainder 2 when divided by 3. All members of sequence cn are multiples of 3, therefore give remainder 0. We need to prove the sequence an contains losing numbers, while sequences bn and cn contain winning numbers. It can be easily seen that all sequences are arithmetic progressions with difference 3. In particular, this applies to an, so let's write an plus 1 equals an plus 3. Now we are ready to prove our statement, and to do that we use induction by n. Base case, n equals 1. A1 is 1 and this is a losing number. B1 is 2 and C1 is 3. And as we've seen before, 2 and 3 are the winning numbers. All that agrees with the statement, and we move to the induction step. We assume the statement to hold for n less or equal than k. So for z values of n, an are the losing numbers, bn and cn are the winning numbers. We need to prove the statement for n equals k plus 1. In other words, that a with index k plus 1 is a losing number, while b with index k plus 1 and c with index k plus 1 are winning numbers. We start with proving that a with index k plus 1 is a losing number, and do that by contradiction. Suppose a with index k plus 1 is a winning number. In this case, a with index k plus 1 can be represented as a sum of 2 or 3 losing numbers. A sub k plus 1 equals p1 plus p2 plus maybe p3. All the right-hand side terms are losing numbers, and they are all less than a with index k plus 1. That means that the induction assumptions apply to these terms, according to which all these numbers can be nothing but members of sequence AN. So we write P1 equals A with index J1, P2 equals A with index J2, P3, if any, equals A with index J3. Consequently, A with index k plus 1 equals A with index J1 plus A with index J2 plus maybe A with index J3. Note that all J indices are no more than k, and without loss of generality, we can assume that they are listed in non-increasing order. Suppose J1 equals 1. Then, due to the non-increasing order, all other J's must be also equal to 1. This means that A's with indices J1, J2, and J3, if any, are all equal to A1, which is 1. So, their sum, which is A with index k plus 1, is no more than 3. However, k is no less than 1, therefore k plus 1 is no less than 2. Since sequence AN is an arithmetic progression with a positive difference, it is increasing. Therefore, A with index k plus 1 is no less than A2, which is 4. This contradicts with the previous inequation. Don't be in a hurry, the induction step is not over yet. The contradiction just shows that J1 cannot be 1. So J1 is at least 2, then J1 minus 1 is a valid index. And we can write A with index J1 equals A with index J1 minus 1 plus 3. From which it follows that A with index J minus 1 equals A with index J1 minus 3. I move the last equation up and wipe out some lines in order to free space. Let's write the expression for A with index k. A with index k equals A with index k plus 1 minus 3, which is A with index J1 plus A with index J2 plus maybe A with index J3 minus 3. However, as we've seen before, subtracting 3 from A with index J1 gives A with index J1 minus 1. Therefore, A with index k is A with index J1 minus 1 plus A with index J2 plus maybe A with index J3. This represents A with index k as the sum of 2 or 3 losing numbers. Therefore, A with index k must be a winning number, which contradicts with the induction assumption. This finalizes the proof for A with index k plus 1. However, the induction step is still not over, as we yet need to prove that B with index k plus 1 and C with index k plus 1 are the winning numbers. Fortunately, nothing can be simpler than that. We just write B with index k plus 1 equals A with index k plus 1 plus 1, and C with index k plus 1 equals A with index k plus 1 plus 1 plus 1. Since it has been already proven that A with index k plus 1 is a losing number, B with index k plus 1 and C with index k plus 1 are the winning numbers. Finally, the induction step is over and the statement is proven. At the start of the game, all piles have 2020 stones. So the quantity 2020 is the only choice for Amy. See what we have for number 2020. We can just add up the digits and get number 4, giving remainder 1 when divided by 3. Or we can take number 2020 itself, which of course also gives the remainder 1 when divided by 3. According to the proven statement, it means that 2020 is a losing number. So unless her opponent back makes a mistake, Amy is doomed to lose the game. The problem number 2 is complete, and we move ahead. Problem number 3. You can never tell with the B's, and you can never tell with the G's, meaning geometric problems. There are always numerous ways to draw auxiliary lines and find out some facts that finally happen to be useless. This problem is not an exception, so it was really a miracle that I could make it. Just reading the conditions without drawing doesn't make sense for a geometrical problem. So I just let you read the problem, make a drawing, and try to solve it. So let's make the drawing together. We have a right angle triangle ABC, where ACB is the right angle. Write it as condition number 1. AC is perpendicular to BC. Then we need to draw the circumscribed circle. However, we are more interested not in the circle itself, but in its center. We know that inscribed right angle subtends the arc of 180 degrees. This means that AB is the diameter of the circumcircle, as the center of the circumcircle is the midpoint of AB. Name it point O and connect it to C. That will be condition number 2. Now let's draw the circumference, and at the center of the circumference, point O is equidistant to A, B, and C. Now we need to draw the tangent line at C, which must be perpendicular to the radius OC. We also continue the hypotenuse AB until the tangent line and the hypotenuse meet at point D. And we write condition number 3. CD is tangent line, therefore CD is perpendicular to OC. After that, we can simplify the drawing by wiping out the circumference, which is no longer needed. What do we have next? E is the midpoint of CD. No problem. We only need to write that down as condition number 4. E is the midpoint of CD, therefore CE equals DE. F is the point on line EB such that AF is parallel to CD. Can we make it? Yes, we can. Firstly, we draw the line EB. Then we draw a line parallel to CD passing through point A. F is the point where these two lines meet. And we write the last condition. Condition number 5, AF is parallel to CD. 5 conditions and only one thing to prove. Prove that AB is perpendicular to CF. Well, AB is obviously the hypotenuse of the triangle ABC. Line CF is not even drawn, and I will not draw it until it's really needed. Now, as the drawing is ready, take another look and think what can be done. We are starting with the very last condition, condition number 5. AF is parallel to CD. You of course remember different angles related to parallel lines. Here we take two angles, angle ADC and angle DAF, which have equal values as alternate interior angles. There's also a pair of vertical angles, DBE and ABF, which are also equal, of course. Guess what I'm going to do next? That's right. Take triangles BDE and AFB. So the triangles are similar by angle-angle rule, and we can write the equation for their sides. AB over BD equals BF over BE. Name it equation 3.1. This equation contains segment BF, which is good, because F is the toughest point to deal with. So we leave the right-hand side as is and see what can be done with the left-hand side. According to the condition 2, O is a midpoint of AB. So we can write that AB is twice OB. Another segment in the left-hand side of equation 3.1 is segment BD, which doesn't have a midpoint. To be more precise, it doesn't have a marked midpoint. So let's mark it and name point G. Let's write condition number 6. Even though it's not quite a condition, I believe that's the right place for it. G is midpoint of BD, therefore BG equals DG. Now we can write BD equals 2 times BG and substitute the values of BD and AB into the equation 3.1. Factors 2 are cancelled out and we get equation 3.2. BO over BG equals BF over BE. See how we can use the equation 3.2. Let's draw segments GE and FO. This brings up two new rectangles, BEG and OBF. The equation 3.2 shows that these triangles have proportional sides, while already familiar to us vertical angles DBE and ABF are the included ones. This time we use side angle side rule, from which it becomes evident that triangles BEG and OBF are similar. Now we, vice versa, use the similarity of triangles to find equal angles. These are angles BEG and BFO. It can be seen that these angles are alternate interior for lines OF and EG with traversal EF. And we conclude that OF is parallel to EG. At the first glance, the fact that the lines are parallel looks meaningless. However, the second look shows something really interesting. E is the midpoint of CD according to condition 4, while G is the midpoint of BD according to condition 6. Therefore, EG is the midsegment of triangle BCD, and a midsegment is parallel to the third line. Thus we get EG is parallel to BC. So OF is parallel to EG, and EG in turn is parallel to BC. Therefore, OF is parallel to BC. But according to condition 1, BC is perpendicular to AC. Therefore, OF is also perpendicular to AC. And that's a real breakthrough. We found that OF is perpendicular to AC. Let's continue line OF until it meets line AC at point H. Due to 3.3, FHA is right angle. Consider triangle AOC. Since side OA equals side OC, this triangle is isosceles, where OH is an altitude to the base. Therefore, OH, which can be also named FH, is the perpendicular bisector to segment AC. Any point of the perpendicular bisector to a segment is equidistant to the endpoints of the segment. Since point F belongs to the perpendicular bisector to segment AC, point F is equidistant to points A and C. Now we can finally draw the segment CF and write down the equation 3.4. AF equals CF. The time has come for segment CF. Maybe we are really close to the end. Let's see. Let alpha be the value of angle BAC. Since triangle AOC is isosceles, the value of angle OCA is also alpha. Believe it or not, there is a condition that was never used so far. Condition 3, according to which OC is perpendicular to CD. And we are going to use it now. So, OC is perpendicular to CD, while according to condition 5, CD is parallel to AF. Therefore, OC is perpendicular to AF. Let's highlight this line along with another pair of perpendicular lines OF and OC according to 3.3. Now consider angles OFA and OCA. The angles have mutually perpendicular sides. Therefore, they can be either complementary or equal. However, they are both acute, being acute angles in right-angled triangles. Therefore, they must be equal. Angle OFA equals angle OCA equals alpha. But there is more to that. According to 3.4, triangle AFC is isosceles, while FH is its altitude. Therefore, FH is also the bisector of angle AFC, which means that angle OFC equals angle OFA equals alpha. Thank you, Alpha, for such a triumphating escapade with the only purpose to establish the congruence of angle CFH and BAC. And we write that down as equation 3.5. What remains is as easy as drinking a glass of champagne. Let K be the intersection point of lines AB and CF. Consider triangles OFK and OAH. They have a pair of equal angles. Angle OFK equals angle OAH according to 3.5. They have another pair of equal angles. Angles FOK and AOH are equal to each other as vertical. Therefore, the remaining angles must be also equal to each other. Angle FKO equals angle AHO. But according to 3.3, AHO is a right angle. Therefore, FKO is also a right angle, which just means that AB is perpendicular to CF, quod erat demonstrandum. To me, it's the best problem out of this contest. But there is yet another problem to solve. Problem number 4. For positive integers n, define sequence A by the following conditions. A1 equals 1, A with index A plus 1 equals AN plus 2 divided by AN plus 1. Another sequence B is also defined for positive integers. For B, conditions are the following. B1 equals 1, B with index n plus 1 equals Bn squared plus 2 divided by 2Bn. Proves that B with index n plus 1 equals A with index 2 to the power of n for all non-negative integers n. This is a bit tough. Take a big breath before we proceed. At start, let's as usual analyze the conditions by taking few static members of sequence A. A1 equals 1, this is given. For A2, we apply the recursive formula, which gives A2 equals A1 plus 2 over A1 plus 1, which is 3/2. Similarly, A3 equals A2 plus 2 over A2 plus 1, which is 7/5. A4 is A3 plus 2 over A3 plus 1, which is 17/12. Looks like we are never going to get a whole number again for A. But one thing is certain, all members of A are rational numbers. Indeed, addition and division are the only operations used in the recursive formula. And these operations, when applied to rational numbers, can give nothing but a rational number. Since the starting member A1 is a rational number, all members of the sequence will be rational numbers. Guess what we are going to do next? So we write AN equals Pn over Qn, where Pn and Qn are integers. And quite obviously we need recursive formulae for Pn and Qn. Let's see what we can get out of recursive formula for A. So we write P sub n plus 1 over Q sub n plus 1 equals A sub n plus 1. Then we apply recursive formula and substitute Pn over Qn for An. Multiplying numerator and denominator by Qn, we get Pn plus 2Qn in the numerator, Pn plus Qn in the denominator. Bearing in mind that A1 can be represented as 1 over 1, we obtain the following formulae. For P, P1 equals 1, P with index n plus 1 equals Pn plus 2Qn. Name it 4.1a. For Q, Q1 equals 1, Q with index n plus 1 equals Pn plus Qn. Formula 4.1b. Using these formulas, it can be proven that both P and Q sequences are increasing and contain only positive numbers. Also, it can be proven that all pairs Pn and Qn are coprime. Therefore, indeed, A1 is the only whole number in sequence A. However, this is not essential for solving the problem, so I will not go into the details. At the same time, I must admit that this formula is not what we really need. We want to express P sub m plus 1 in terms of previous members of P sequence, and Q sub m plus 1 in previous members of Q sequence. What we see here is a weird mixture of P and Q. So let's do the following trick. Subtract equation 4.1b from equation 4.1a. We get P with index n plus 1 minus Q with index n plus 1 equals Qn. From where we find that P with index n plus 1 equals Q with index n plus 1 plus Qn. This is formula 4.1c, which is not clear yet, but there is another trick in our reserve. Take formula 4.1b and write it for Q with index n plus 2 by shifting the indices one up. So we get Q with index n plus 2 equals P with index n plus 1 plus Q with index n plus 1, and name it 4.1d. Then we substitute P sub n plus 1 from 4.1c into 4.1d. Ta-da! All the p's have gone. We only need to simplify that by merging similar terms and add starting values, which are Q1 equals 1, Q2 equals 2. Thus, we get formula 4.2b, reserving 4.2a for P, of course. For sequence P, we do in similar way. This time we need to get rid of Qn, therefore we multiply 4.1b by 2 before subtraction. Factor 2 before Q sub n plus 1 is not really a problem, take it as is. And we get formula 4.1e for 2Q with index n plus 1. Then we add 1 to the indices in formula 4.1a and get formula 4.1f for P with index n plus 2. Substitute 2 times Q with index n plus 1 from 4.1e into 4.1f and get the recursive formula for P. After adding the initial values P1 equals 1, P2 equals 3, we get formula 4.2a. With recursive definitions of P and Q, we proceed to the next stage. Believe it or not, that was the toughest part for me. All the rest went nice and smoothly. So we got to sequences Pn and Qn defined recursively. What is quite amazing here, both sequences have the same recursive formula. They only differ in second starting values, P2 equals 3 and Q2 equals 2. Our objective is to convert them into closed formulae, and fortunately there is a standard technique for that. Sequences of this type are called linear recursive sequences, as the right-hand side of the recursive formula represents a linear combination of the preceding members. In our case, there are two initial values, consequently two preceding members in the right-hand side of the recursive formula. It can be written in general as C1 equals V1, C2 equals V2. C with index n plus 2 equals A times C with index n plus 1 plus V times C with index n, where initial values V1 and V2 are of course constants. Coefficients A and B are also constants. Note that elements of the sequence appear in the recursive formula in decreasing order of indices, n plus 2, then n plus 1, and finally n. To get a closed formula for such a sequence, we write a so-called characteristic equation. By replacing members of the sequence with a variable in different powers. Usually Greek letter lambda is used for such a variable, but oddly enough I have technical problems with using letter lambda in expressions, so I will use Hebrew letter gimel but call it lambda. My apologies to Greek and Hebrew alphabets for such a nonsense. The power of lambda is written also in decreasing order. So the characteristic equation is lambda squared equals a times lambda plus b. Equation 4.3. This is a quadratic equation for lambda and it has two roots. Here we only consider the case when the roots are real and distinct. The closed formula for Cn is written as Cn equals k1 lambda 1 to the power of n plus k2 lambda 2 to the power of n. Equation 4.4, where the constant factors k1 and k2 are selected according to the initial values, v1 and v2. And since the initial values are always met, we only need to check that the sequence defined by equation 4.4 satisfies the recursive formula. So they take the difference between left-hand side and right-hand side of the recursive formula and show that the difference equals 0. To do that, we evaluate each term of the sequence using equation 4.4. Then we group separately terms with lambda 1 and lambda 2. Since lambda 1 and lambda 2 are roots of the characteristic equation 4.3, the expressions in both brackets are zeros, so the whole expression is really 0. This proves closed formula 4.4. Before moving on to Pn and Qn, one minor observation. Adding same value to powers of both lambda 1 and lambda 2 in equation 4.4 changes only factors k1 and k2. What I really mean is the following. If alpha is an arbitrary number, positive or negative, formula 4.4 can be rewritten in the following way. Then we introduce new constants k1' and k2', and get a formula very similar to formula 4.4, where the powers of lambda 1 and lambda 2 are shifted. We will use this formula with alpha equals -1 and call it formula 4.4a. Now back to our Pn and Qn. Since they have same recursive formula, we need only one characteristic equation. Lambda squared equals 2 lambda plus 1. Making it look more appropriate and find the roots, 1 plus minus square root of 2. They are same for P and Q, however the factors will be different as the initial values differ. Now we can write the closed formula for P and Q using 4.4a, where factors a and b still need to be found. That will be formally 4.5a and 4.5b. So let's find the factors. To do that, we get Pn and Qn for n equal 1 and 2 and equate them to the initial values. When n equals 1, all the powers in 4.5a and 4.5b become 0. So P1 is just a1 plus b1 and Q1 is a2 plus b2. Since P1 and Q1 are 1s, both expressions need to be equal to 1. Now you see why I use power n minus 1 instead of n. This simplifies the equations for the factors. For n equals 2, we get something much more complex for P2. But as we already know that a1 plus b1 equals 1, the expression can be simplified. A similar expression we get for Q2. We know that P2 equals 3. This gives the following equation, from which we find that a1 minus b1 is square root of 2. Q2 equals 2. So the equation for Q2 will be slightly different. Here we find that a2 minus b2 equals 1 over square root of 2. We've got two simple systems of simultaneous equations for a1 b1 and a2 b2. And we solve them. Now the closed formulae for P and Q are completely defined. As you probably noticed, we can simplify the expressions by merging factors, adding their powers. So we got the closed formula for Pn and Qn, and we can write the closed formula for An. Formula 4.6 is hardly believable, but it produces a rational value for any positive integer. Now it's time to recall what the problem is about. We have another sequence, for goodness, Bn, which is also defined recursively, and the recursive formula is not a linear one, so I doubt that we can find a closed formula for Bn. And what do we need to prove? B with index n plus 1 equals A with index 2 to the power of n for non-negative n. That's very weird. As a computer programmer, I don't mind counting from 0, but since A and B are defined from 1, let's be consistent. And so we will. Let m be n plus 1, so when n counts from 0, m will count from 1. Then n equals m minus 1, and the substitution gives b sub m equals a sub 2 to the power of m minus 1, where m is 1, 2, etc. What a relief. And guess what? We replace letter m with letter n. So we get a consistent equation to prove. I really cannot find a logical explanation why the equation wasn't originally given this way, unless they had technical issues with 2 to the power of n minus 1, similar to what I had with lambda. Anyway, we are now on the right track, so let's define sequence Cn, which is A with index 2 to the power of n minus 1. We need to prove the sequence C is the same as sequence B. In other words, Cn equals Bn for any positive integer n. We start, of course, with checking the initial values. C1 is A with index 2 to the power of 0, which is A1, which is 1, which is equal to B1. Now we need to check that the recursive formula for sequence B applies to sequence C, which means that C with index n plus 1 equals Cn squared plus 2 over 2 times Cn. Name it equation 4.7. Let's get the formula for Cn. To do that, we replace in formula 4.6 n with 2 to the power of n minus 1. Does the formula look terrifying to you? If not, try to continue from this point. We can make the formula less scary by introducing two auxiliary sequences. Fn equals 1 plus square root of 2 in the power of 2 to the power of n minus 1. Gn is similar to Fn, but it has minus square root of 2 instead of plus square root of 2. This allows to write Cn as square root of 2 times Fn plus Gn divided by Fn minus Gn. And this will be formula 4.8. Let's find the recursive formulae for Fn and Gn. F with index n plus 1 is 1 plus square root of 2 to the power of 2 to the power of n. 2 to the power of n can be represented as 2 to the power of n minus 1 times 2. And of course, when a power is multiplied by 2, it can be replaced by taking a square. And as you certainly noticed, the value in square brackets is just Fn. And we find that f with index n plus 1 is Fn squared. In the similar way, g with index n plus 1 is Gn squared. And we are finally ready for the last step, to prove formula 4.7. We write the formula for C with index n plus 1 and apply the recursive formulae for f and g. You've noticed that the denominator can be factorized. But leave that for now and take care of the numerator. So we divide factor square root of 2 by 2 and also multiply the numerator by 2. Here is the smart part. The numerator can be represented as the sum of two squares. To check that, you can just distribute both squares and reduce similar terms. And as you can see, this time we did factorize the denominator. If we split the fraction by dividing term by term, we get in the brackets a sum of two mutually inverse terms. It can be easily seen that the first term is Cn divided by square root of 2, while the second term is the inverse of that. Then we move to the common denominator, simplify, and here it is! After all, we did find the closed formula for Bn. It is the same as for Cn. There is only one sad thing. The video has come to the end.